LADEE, LADEX Derived Gardening Rates.
Sounds good. All right, so today I'm going to be talking about meteoritic gardening and the amount of dust that we measured raining back onto the lunar surface using the data from the LADEE mission. We're able to make measurements at the moon of the dust cloud because the moon's being continually bombarded by micrometeoroids. So typically these are categorized into two different groupings from Earth. You have the meteor showers. These are particles that have been lost from their parent bodies, but they still track, they still follow similar orbits. And so as they evolve, slightly different from their parents, they form a tube-like structure in the solar system. And if Earth's orbit happens to intersect that, we get a meteor shower. Now, some of these particles, they're ejected a little more violently, or they're a little older, they've had more time to evolve, and they lose memory of their parents. And they form these sporadic meteoroids that if you see a shooting star on a random day, it's probably a sporadic. But they're not completely isotropic. They actually also come from certain directions. So in the ecliptic plane, we see groupings coming from the sun, coming from away from the sun, the antihelion, and coming from the apex direction, the direction we're traveling with respect to the sun as we orbit. And so today's talk is focused on what happens when impacts kick up the dust from the moon and then it rains back down in a process called impact gardening. This is relevant for a couple different issues on the moon. I've highlighted three of them here. Number one is lunar swirls. So many of you are familiar with this. They're these interesting albedo markings. There's a couple different competing theories. This is an image shown from Garrick Bethel et al., one from Papi et al. And whatever the explanation for these interesting albedo markings, they have to stand up to being continually covered back up with lunar ejecta. Additionally, I think many of you are familiar with the Siegler-Miller-Keene et al. Paper from 2006. With lunar polar wander, they were able to measure this interesting signature at the pole. This also speaks to the gardening rate that's going on. You could almost flip it and say that because they were able to make this measurement, that informs us on the meteoritic bombardment in the high latitudes. And lastly, we've put instrumentation on the moon. So the lunar laser, the retroreflectors placed on the moon during the Apollo era have been noticed to significantly degrade. One interpretation of that is that it's covered by approximately 50%, possibly by dust. And so this somehow has to fit into our understanding of gardening and dust mobility at the lunar surface. So briefly, the way we were able to measure the dust at the moon is with an instrument called LDEX, the Lunar Dust Experiment. This is an impact ionization dust detector, such that you have an impactor coming, it hits the surface of the moon right here, it kicks up a bunch of dust, and we are able to measure it as it hits this hemispherical detector that's orbiting the spacecraft. It generates electrons and ions, and we can get both of those out as signals. Here's the ions, here's the electrons. So we get signals for every impact, and we're able to get the mass, an estimate of the mass for each impact. We can take all the impacts we ever got, and we can make a map of the dust density distribution over the whole lunar surface. The areas here shown in black are times that we were either not able to make a measurement or we were not on. And there's a couple interesting features of note here. Number one, it's asymmetric with respect to the apex direction. And by that I mean if that's the direction to the sun, and we forget about Earth, the moon is orbiting the sun in that direction, its orbital velocity. And the most dust we see is in the apex direction, the ram direction, right on the windshield. Not only that, but it's also kicked over towards the sun. And this was an unexpected result and something that we worked to understand. And it turns out that those sources in the ecliptic plane have different amounts depending on the time of year. So if I'm the moon and you guys are the sun, there's the three sources that we understand are if you have a grain that's orbiting with a higher eccentricity than Earth, as it visits the sun and it goes back out, it'll hit you on the left side, this blue helion, And then as it goes out and it comes back towards its perihelion, well, then you get an antihelion source, red shown here. The third one would be the apex direction. Those are grains going against traffic. They're retrograde, and they hit you with a really high velocity. And it turns out that by summing just these three sources, we're able to explain the shape of the lunar dust cloud with reasonable accuracy. And so we think we understand that the structure we see is coming from these three sources in the ecliptic plane. Not only that, but as the moon now orbits the Earth, and it's running into some of these or running away from some of these, the dust cloud actually breathes. It waxes and wanes with lunar phase in such a way that when it's running into the two most prominent sources, the apex and the helion, so when the moon's going that way, you see the plumpest dust cloud. You see the thickest dust cloud. And then as it goes around the Earth and it starts running away, well, that's when the dust cloud is the least dense. We also notice an annual variation, so it's not constant with respect to time. For example, early in January, you see this cant towards the sun is pretty prominent, but as we took measurements throughout the months until April, where we impacted the moon, April we notice an almost symmetric distribution about the apex direction. It turns out this is consistent. Oh geez. I don't think that was me. So this is consistent with what we've measured at Earth. So Earth has radar that measures the source, different amounts of the sources. And if we take the ratio of, say, the helion and the antihelion, this is what we get, what LDEX gets. It's about 2, and then it ends approaching 1. And from ground-based measurements, we start a little lower, 1.5, and it approaches 1. And so qualitatively, it's consistent, and within a factor of 1.5, we're consistent with Earth-based measurements. So that was a brief overview of what we've understood about the lunar dust cloud. And now the question is, how do we calculate how much lunar dust is falling back down onto the surface? So to do that, we need to make some estimate of the total global dust density distribution. On a first cut, what you could do is you could take just the times we measured, and you could collapse them all down into one dimension. And that's what's shown here. So that's if we just take each one of these rings is given altitude, and if you collapse them down onto a flat plane, you get this structure. And this puzzled us for a while because you'll notice it's non-monotonic. You see a decay as you should. It's more dense towards the surface, less dense up here. But then you get this bump at the high altitudes. Well, it turns out that because we measure in an asymmetric way in local time dependence, and the moon is asymmetric, that we're weighting different altitudes, different amounts. So if we pull that apart, and I only show an altitude distribution for each local time, so in this shock top logo looking diagram, you can see the color corresponds to the local time, and here's the altitude profile for each local time. And to within very good accuracy, it actually fits an exponential distribution. Again, this is unexpected, and it's not commensurate with the interpretation from the Galilean moons, but it's a very interesting measurement nonetheless. And when we now pull apart the local time dependence, here's just one cut of local time and an altitude distribution. Our exponential fits essentially perfectly. And so we think we are well representing the lunar dust cloud. So we take our measurements and we say, on average, what does the cloud look like? And so in some periods of time, the helion's stronger, some the antihelion, and for the sake of calculating gardening, we pick a distribution that is symmetric. And so this now is our average cloud fit, shown by this equation. It's an exponential in altitude, it's a power law in particle size A, and you've got the sum of 4 different sources, helion, antihelion, apex, and then there's a small one hitting you in the back. From that, we can then calculate the velocity distribution. So if we know the altitude distribution, we can calculate, well, what velocity did either the grains start, or what velocity will they then rain back down onto the surface? It's the same thing. So shown in green here is the derived velocity distribution function for the lunar dust. In addition, this is really interesting because this very well may be indicative to the velocity distribution at many airless bodies. We measured this at the moon, but this could be a more fundamental measurement with respect to what velocities we're seeing come off asteroids, Phobos, Deimos, and so forth. So with this velocity distribution, we can then convolve that with the density and calculate how much dust is raining back down onto the lunar surface. That's shown right here. This is the product of the density you saw before, but now times the velocity that it's going to hit if it's starting at that altitude. And so this is essentially the rain cloud at the moon of dust. And unsurprisingly, it is the strongest at the apex direction, and it wanes off on either side. Then you could integrate this in altitude, and that's what's shown here in this plot. And so you get, as a function of local time, what flux does the moon receive? And then you could integrate one more time and get the average flux. That's this dotted line. It's about 1 hit per meter squared per second, times, and then depending on the particle size. So lastly, we have the flux hitting the surface. Now we need to figure out, well, how much total material is covering the surface? How much is that contributing to the surface? And so the first step is calculate the characteristic size. So we have a particle distribution function. That's another really interesting measurement that LDEX was able to make. So we can tell you that the size distribution of the dust falling back down onto the surface, the cumulative size distribution, has an index of 2.7. So we know what size distribution is falling back down onto the moon. We then calculate the average cross-sectional area, and from that and the flux, we can calculate the total accumulation depth. So the last parameter that might be important is the characteristic size. We were able to measure particles down to 0.3 microns, but it's unlikely that that's the lowest size grains that are being lofted up by meteorite impacts. So we looked at this as a function of lowest characteristic size, assuming that power law holds. And fortunately, the results are not that sensitive. It goes to the size to about the 0.3. It's not so sensitive. And so the main result then of this work is the accumulation depth. And that's that from meteoritic bombardment, approximately 40 microns per million years is redistributed in the ecliptic plane on the lunar surface. So in conclusion, we were able to derive a fit for the entire equatorial lunar dust density distribution. From that, we're able to calculate the gardening rate, so we can figure out that about 40 microns per million years is recovering features on the lunar surface. And this helps constrain a few different things. One of them is that any explanation for the swirls has to fit within this amount of dirt being reshoveled back on. It turns out that the amount of material needed to cover the retroreflectors is nowhere near, is significantly higher than what we calculate by many, many orders of magnitude. And also similar processes take place on all airless bodies throughout the solar system. Of course, the smaller the body, the less it's going to rain back down. It'll be lost. And lastly, we still don't constrain the low altitude dust mobility. So the surveyor images are not discussed on this, and it's conceivable that the retroreflectors the degradation is due to large volume of low altitude, maybe electrostatic, maybe low altitude ejecta. So with that, I'll take any questions. Thank you.
Thanks, Jamey. That was a great talk. The question I've got is, I was trying to figure out how 40 microns per million years, how much stuff that really is. And then you said something that really puzzles me. If that isn't nowhere near enough to have covered the retroreflectors just in the time that we've left them on the moon to now, then why do we think that that would be any problem at all for the lunar swirls?
So
it seems like it wouldn't be much of an effect.
Yeah, so the retroreflectors have been there for approximately, say, 40 years. And the swirls, as far as I know, the lifetime and the aging is a process that takes place in a much longer time scale. And so while 40 years is a very short amount of time, The swirls, the time scale in which space weathering applies to them is somewhere in this regime, and I don't know that number, and I'd be thrilled to talk to someone about that, but we're talking millions of years kind of time scale. Yeah.
Hey, Jamey, great talk. One question I have is that dust local or non-local in that layer? In other words, are the grains going up straight up and coming back down so they haven't really moved, or are they going off and, getting 200 kilometers high but then coming down 400 kilometers? So how local, is there really distribution? I mean, really is what we're talking about.
There is. So that's something unpublished yet that we're still working on, and that's constraining kind of the realm of applicability, and that's how big the cone is, how high they go up. An initial, say, estimate is that you're talking hundreds of kilometers that they spray out onto on either side.
Cool.
So it's a pretty big swath.
Sort of following up on that, I've got to think, this is really interesting. I've got to think about it some more. But sort of going back to what Yvonne was asking about, seems to me over the billions of years that a surface has been exposed, you'd get a couple of maybe tens of microns thickness, which should optically remove a lot of the features, and we don't see that. So I'm either missing something or you are. I've got to think about it, but I'd be interested in what you have to
Sure.
react
So
to.
I can respond with two comments, I guess. One, I can only report to you the measurements that we take, and in doing my best to self-consistently say, I see this much, how much is falling back down?
Yeah.
So that's what I'm reporting. Additionally, this is applicable for periods of time in which the bombardment is similar to now. Although it's kind of going the other way of that argument,
Yeah.
because if there's more bombardment earlier,
Yeah.
you see more. But also at high latitudes, not the equatorial plane, you should get significantly less bombardment, because the equatorial plane is, all the planets live there, most of the dust lives there. And if you want to get hit on the top of the head in a permanently shattered region, you have to have a particle with a 90-degree inclination.
Could there be a recycling, though, so it's not just an accumulation, that some of the stuff that comes down ends up going back up again?
Sure.
So maybe that's the way to deal with it.
Well,
Okay.
Doug Curry, University of Maryland. I am surprised, as some of the others are, at the low rate. I believe this is far less of a rate than the diviner people have found as far as looking at rocks that have come out from recent impacts. I think they've found for 1 million years a much greater rate, and certainly our corner reflectors have seen a greater rate. And my very naive back of the envelope calculations on the LDEX data showed thicker, so I'd like to talk to you later on that.
Sure.